Assalamu alaikum. Welcome, students. This is the fourth lecture in the series of lectures of CS-241 machine learning offered to the 8th semester students of the HSFI University. This is the second video lecture. The first two lectures are considered to be the lectures that were given in the class. So today we are going to study the vector norms and the overall understanding. We are going to look at about the norms, what are norms, how do they, why are they important, what are they representing. Okay, let's start by the first definition of uh, the distance formula, which you already know, but let's start from the very basic. So let's build up the lecture with the basic topic of distance formula. So you have already studied what is a distance formula. Distance formula is actually it gives you the distance between 2 points. So these 2 points can be the head of a vector and the tail of a vector. So the distance formula is actually originated from the Pythagoras theorem, where you can find the length of the third side of a right triangle if the other two sides are given. So this formula actually gives you the length of a vector from the origin. So considering that we have a vector v having a point v in the vector space of Rn and the tail at the origin. So the distance formula gives you the length of this vector from the origin. So you can see this formula v minus a 0 vector. Actually we are subtracting the distance of the head of the vector, subtracting the origin from the head of the vector. So you can see this formula boils down to a simple the under root of the sum of the squares of the values of the head of the vector. Okay, now there is another name for this distance formula, which is also called the Euclidean distance, the Euclidean norm, or the L2 norm, represented by the two parallel line symbol and a subscript of 2. So the subscript of 2 represents the norm, the parallel lines represents the norm, and the subscript 2 represents the L2 norm, or the distance formula, or the Euclidean norm. So it is the same thing as the distance formula you have seen before. So you can look at the preceding equations, how this is formed. So this is the most used norm, the distance formula. So it is often used without the subscript 2. So whenever you see a norm of any vector or a matrix without a subscript, it means that we are talking about an L2 norm. So let's move on and look at the explanation of this. Okay, so when we are talking about the norm of or the distance between two vectors, what are we talking about? So if we see the previous example where we used the 0 vector representing the origin, we can replace the 0 vector with the other vector. So as you can see in the figure, we have two vectors, a vector v and a vector w, in a three-dimensional vector space, that is R3. So the distance between these two vectors is actually the distance between their heads, respective heads. So you can represent it in the equation similar to the previous example that you have seen. So the distance is actually the difference in the components of the respective components of the head of the vectors. So you can see, like for example, since we are talking about R3, so R3 means that each vector will be represented by an x component, a y component and a z component. So in the distance formula, we are going to subtract the respective elements of the two vectors. For example, for the vector v, we will have v1 component representing the x component, v2 representing axis, v3 representing the z axis. So we are going to subtract the respective components of each vector, that is v1 minus w1, v2 minus w2, v3 minus w3. So you can see the formula has shrinked to three components because we are dealing with the distance between two vectors in R3. Hope it is very much clear. Okay, let's look at the inner product. Okay, it's also known as the dot product, but the difference is not very much in the dot product and the inner product. Normally, dot product is related to the product of vectors in the subject of physics, and it has a proper derivation, and the term inner product is normally used in linear algebra between the product of two vectors. Let's look at how this inner product is related to the Euclidean norm or the L2 norm. So you can see here that the dot product is represented by this formula. So if you see that we are taking a dot product of a vector by itself, a vector v having a dot product by itself. So what is actually happening here, since a vector is having a product by itself, so the angle between itself is 0. So that's why we are left with only this product, which is actually the square of the L2 norm. So we are skipping the subscript here. So it is the square of the L2 norm, also called norm squared. So the dot product or the inner product of two vectors is actually the square of the L2 norm or the square of the Euclidean norm or the distance formula. Okay, another view, let's take another view of the dot product, which is actually how would we claim this product of two vectors to be similar to the dot product is by multiplying a row vector and a column vector. So in terms of matrices, if you see that this vector has a dimension of 1 by 3 and this vector has a dimension of 3 by 1. So we can safely multiply these two vectors or matrices, and the product would be 1 by 1 matrix or a scalar value. So let's see what do we get when we multiply this. So we are getting the same thing, which is actually what? It is the norm squared. So if you remember from the previous slide, we had under we had a square root sign above this. So if we square this, square root will cancel by the square. So this thing is actually the norm square, which is actually this. So this is how the inner product and the dot product are related. So let's look at the inner product of two different vectors. So as we have seen that the inner product is actually the dot product. So when the angle between two different vectors, let's say v and w, is 0, that means considering two vectors v and w originating from the origin. So when they are superimposed, their angle between them would be 0. So their product will be the product of their lengths. Since theta is 0, so this term will be 1. On the other hand, if these two vectors have a theta of 90 degrees, so this relation will become 0 because cosine 90 is 0. So you are left with a 0. So theta of 90 signifies that the two vectors are perpendicular, or a more famous name, orthogonal, is used. So orthogonal vectors means that they are not, their components are not affecting each other. So this is the basics of the inner product and the dot product that will be used in the future in a lot of matrix manipulation. Okay, let's look at the dot product in when we are multiplying two different matrices. Okay, now let's find out where is the inner product in matrix multiplication. Okay, there are two ways you can find out the matrix C: by multiplying matrix A and B. Now the first way is to multiply the rows of A with the columns of B. So this will give you a single element of matrix C. As it is visible, if we want to find out the first element of matrix C, that is C11, it is actually the dot product or the inner product of the first row of matrix A and the first column of matrix B. So how it works, it is the product of A11 B11 plus the product of A12 B21 plus the product of A13 B31, which is shown here in this mathematical formula, how the element C11 is generated. So in terms, this summation is the scalar view, but in terms of vector views, we can show it as this inner product. So this inner product is actually producing a single element of matrix C. So you can see that in matrix multiplication, you are actually taking the inner products of the rows of one matrix and the columns of the other matrix. So let me make one thing clear. Now, vectors normally in the literature are taken or and considered to be as a column vector. So whenever you want to change the dimension of the vector, that means a column vector is represented by n times 1. The dimensions of a column vector is n times 1. So if you want to make it a row vector, you will take a transpose of that and make it a 1 by n. So that's why a row vector is always written as uh, in the form of a transpose. Okay, let's look at the other way which you can find out the product of two matrices A and B. Okay, before we do that, let's go through an example of a matrix multiplication using the inner product. So here we have taken two matrices A and B, and we are going to multiply them to find out the matrix C. So you can see that C11 is actually the product of the first row of A and the first column of B. So let's multiply. So this is A11 times B11 and A12 times B21. So this is 2 plus 0, that is 2. So this is your 2, C11. Similarly, C12 is 1 times 4 plus 0 times 5, which is 4. This is your C12. C21, which is 6 here. Let's see how it came to be 6. 3 times 2 is 6 plus 1 times 0 is 0. So it's 6. C22 is 3 times 4, which is 12, plus 1 times 5, which is 5, which is 17. So we have the matrix C. Let's look at the other method of finding out the product of two matrices, which is also called finding out the outer product using the outer product method. Now what is an outer product? Now outer product, or in physics the cross product, is actually the product of two vectors making up a matrix. Now it's a bit opposite of the inner product. Okay, let's consider the outer product of the columns of A and the rows of B. So let us treat the vector A to be the first column of A and the vector B transpose to be the first row of B. So the dimension of the first column of matrix A is 3 by 1, and the first row of matrix B is 1 by 3. So the column of the first matrix matches the row number of rows of the second. so we can multiply, and the number of rows and the number of columns, they make up the dimensions of the output matrix. So definitely we are going to have a 3 by 3 matrix in return. So this is the first outer product. Okay, so we are going to, this is the first outer product. So next outer product would be the second column of A and the second row of B. The third outer product would be the third column of A and the third row of B. So it is visible here in this formula. So since it's a 3 by 3 matrix, the output is also 3 by 3. Both A and B are 3 by 3, so the output will also be 3 by 3. So it's a sum of the three outer products of the matrices. So this matrix that is being generated as an outer product of the column of A and the row of B is also called the rank 1 matrix. Now, why it is called a rank 1 matrix? As you remember, a rank 1 matrix is a matrix that has a single independent column. So if you see a big picture, let's take this column as the independent column. So all the other columns are made of this column. How? I can represent this as the product, this column multiplying this separately. So the base column is this. The new column that is being made is the product or a scaled version by B11. The third column is a product or a scaled by B12. The third column is scaled by B13. So basically this whole matrix is a linear combination of these three terms and this vector. Okay, so this is a single column which is independent, so that's why these outer product matrices are called the rank 1 matrices. Let's look at the example. So let's take the first column of A and the second and the first row of B. So 1 times 2 is 2, 1 times 4 is 4, 3 times 2 is 6, 3 times 4 is 12, plus the second column of A and the second row of B. So 0 times 0 is 0, 0 times 5 is 0, 1 times 0 is 0, 1 times 5 is 5. So these are the two rank 1 matrices. Now you can see here, this is a rank 1 matrix. Okay, now in terms of this and this column, now you can see the second column is made from the first column. If you multiply 2 by this column, you are going to get this column. And in other words, you can see this column is also made from this column. If you multiply 2 by this column, you are going to get this column. Okay, so if you add these two outer products similar to this formula, you are going to get the actual product, the matrix C. Now something here, if you see, which will be used probably in the higher topics, the first outer product is more or less contains the most of the information. So this knowledge is going to be very crucial in the coming chapters. Okay, let's look at some other norms, some other famous norms. So we have gone through L2 norm. Let's go through the L1 norm. So what is L1 norm? Now L1 norm is, as stated, is the sum of the components of a vector. So what are the components? What does component means? So a simple explanation of this is the sum of the distances of a vector from the coordinate axes. Now if you see the red dotted line, now let's look at the vector 1, 1, 1. So it's coming out from the origin, and the distance from the axis. Now let's say this red line represents the distance of this vector in the x direction from the origin. This value plus this value, the distance of the vector in the y direction, and this value, the distance of the vector in the z direction. So we are adding all these three values to get the L1 norm of a vector. So these are two separate stories now. L2 norm, the story is closed. Now this is L1 norm. We are talking about the L1 norm. So L2 norm actually gives you the distance of a vector, or the length of a vector, or the distance between the two vectors. L1 norm is also giving you a distance, but in some other aspects. Okay, so okay, let's think a little bit now. Now for example, if I have a smaller vector, let's say a vector having coordinates 0 0.5, 0 0.5 and 0 0.5. So the sum of this vector would be, sum of the components of this vector would be definitely smaller than the uh, vector with the components 1, 1, 1. So the thing that is coming in the next slides and the next lectures would be to find out the vector having a minimum L1 norm. Similarly, we will find out the vector with the minimum L2 norm. So the minimum it is, the better would be the result. This is the basic idea uh, behind the solution of system of linear equations that we are going to see. Okay, let's see an example of an L1 norm in two dimensions. Okay, now a two dimensional space represented by the x coordinate and the y coordinate. Okay, so this is just to explain you. We can expand this explanation to any number of uh, vector space. Okay, so figure 3 explains the position of a fixed norm vector space. Like for example, let's take a two-dimensional vector having components v1 and v2, v1 representing the x component and v2 representing the y component. So if I say that I fix the norm of if I fix the norm to 1, that means when I add v1, the x component and the y component, the answer should be 1 or less. Okay, so let's talk about a norm of exactly 1. That means when I add v1 and v2, the answer should be 1. So I'm talking about the boundary of this diamond. Now how do I get this diamond? Okay, so let's start by a vector starting from 0 on the x-axis going till this point 1. So what are the coordinates of this point 1? It's 1 and 0. So when you add these components 1 plus 0, it becomes 1. So it's a L1 norm of this vector is 1. So it's all right. Now if I move this vector up here, so it should come on this line. Why? Let's see. If I move this vector to this point, now this point is actually an increment in the y and a decrement in the x, so that the sum of the components is 1. Similarly, if I move this vector to this point, now here as I am increasing y, I am decreasing x, so that the sum of these components remains 1. Are you getting it? So if I fix the norm, I'll for L1 norm, I'll get a diamond. I'm fixing the norm to 1. Okay. So if I say if it's less than and equal to 1, so I am including all those vectors also whose values when they add up are less than 1. So that's why this whole diamond is colored. It's filled with vectors having lengths of 1 and less. Okay, so here the word length, don't mistake it with the distance of the vector. Okay, it's basically the L1 norm. Okay, now with respect to distance, you have to see the L2 norm. So in a 2 dimension, what would be the L2 norm? Now L2 norm is what? L2 norm is the square root here and the squared components. Okay, so less than equal to 1. Let's fix the L2 norm to 1 as well. So which is actually the equation of the circle. So if I square the both of these sides, so I get rid of this under root sign, and if I square 1, it will remain a 1. So v1 squared plus v2 squared less than equals to 1. So what are we saying? We are saying that whenever we square the individual components of a vector and we add them, it should be less than or equal to 1. So if it's equal to 1, it will be this circle of radius 1. Okay, so whenever we are on this point, the L2 norm is always 1. L2 norm is always 1. Okay, so L2 norms gives us a clear circle and L1 norm gives us a diamond shaped figure. Okay, let's look at it in with an example. Okay, before we go to the example, let's just go through some more famous, some of the remaining norms, which are also very important. The L infinity norm. L infinity norm is represented by the infinity sign, which actually says that pick up the maximum value among the components of the vector. So for example, if you have a vector in 3-dimension space, its components are 1, 2 and 3, let's say. So it's one it is 1 in the x direction, it moves 2 in the y direction, and it moves 3 in the z direction. So the L infinity norm would be 3, just the maximum value among these components. Okay, the Frobenius norm of matrix A. So it's a norm of a matrix. So according to the formula, let me explain the formula. It's not that difficult. It's a simple. You squared all the elements of a matrix and add them together and take a square root. Okay, let's look at the Frobenius norm of a matrix A. So you just square the values the individual values and add them and take a root. So the norm squared would be if you are getting the answer without the square root. Okay, it's that simple. Okay, let's look at the example here. Okay, now let's look at this figure, figure number 5 and figure number 6. Okay, so let's take an example. Let's take an equation of a line 3v1 plus 4v2 is equals to 1. So let's solve this so that the distance from the origin to the solution or the vector is minimum. The solution is any point on the line in figure 6. Okay, now this, when you plot this equation, you are going to get this one, this line. So this is, let's say v1, this is representing the x-axis, v2 represents the y-axis. So any point on this line will be the solution of this equation. Okay, so for example, if I take this point, this point is like 0.1, 0.2, 0.3, 0.4. So this is 0.25, something 1 upon 4. So it's 0 in this direction and it is 1 upon 4 in this direction. If I put this in this equation, it's 0 here, so it makes this 0, and if I put 1 upon 4 here, so 4 cancels, you'll get a 1. So any point on this line is actually the solution of this equation. Now any point means any vector. So what do I mean by that? So let's take any point here. So if I make a vector from the origin to that point, so it's a vector now. So the vector, any vector that ends on this line is a solution to this equation. Is this thing clear? So the point is that we will be having infinitely many vectors that will solve this equation, isn't it? I can have a vector starting from 0 to this point, to this point, to this point, this point, anywhere touching this line. That vector will actually solve the equation. But the question is, find that vector which is the smallest in the length. Okay, so this question is treated differently for different norms. So if you're talking about uh, L1 norm, okay, so let's tackle this problem one by one by using uh, first the L1 norm, the L2 norm, and then the L infinity norm. So L1 norm, what we are going to find, if we are looking for the smallest L1 norm vector that solves this equation, is by starting to make a diamond representing a particular L1 norm space. So let's start by expanding that diamond, and you'll see that a point will come when this diamond is going to touch this line at this point. Okay, so if you see from the origin, this is the smallest point, because from here, let's take this point, this is bigger, this is bigger, more bigger, this is more bigger, touching this line. So this, using L1 norm, so L1 norm finds out this vector, which is 0, 1 by 4, to be the smallest vector that solves this equation in terms of L1 norm. Okay, so it is also called the sparse solution. Sparse means that you have, in this solution you have a 0 and non-zero values, maybe more zero values. Okay, let's look at the solution given by the L2 norm. So what we are going to do, we are going to uh, increase the norm of the vector space, okay, and keep on increasing until the norm that touches the first point or the tangent to the circle. Now this point will actually represent the smallest vector solution. Okay, now look at why it is the smallest. Okay, it's a perpendicular, it's actually the perpendicular line. Now let's take another vector which starts from 0 and touches this line other than this point. Let's look at this point. Let's follow this hand. Now this point is a bigger in length. Any point other than this point would be bigger in size. So this point is the smallest vector solution provided by the L2 norm. Okay. Similarly, L infinity norm. It works on the same principle. So as I've mentioned in the last sentence, this will provide us with the solution closest to the origin in terms of the norm used. So these actually these all techniques have a profound effect on the overall solution finding mechanisms. Okay, so this lecture was basically on the vector norms and how will they be used in the coming lectures. So it's a this lecture will give you an idea how they will be actually helping us to solve the system of linear equations. By the way, this picture is a courtesy of the book that I have been using to teach this lecture, by the book written by Gilbert Strang, The Linear Algebra and Learning from Data. So thank you for this image. Okay, students, that's all for this lecture. I will be I'll meet you in the next lecture, lecture number 5, shortly, inshallah. That would be explaining the linear system of equations. Okay, thank you very much.